And hello everyone, my name is Yuhan Zhou. I am a first-year PhD student from Peking University, advised by Professor Chenren. And today I am presenting AUGUR, our multipath transport service for low-tail latency in real-time streaming. And this is a collaborative work with Tencent Corporation when I was an intern supervised by Honghao Liu. So our subject, interactive mobile real-time streaming, is getting popular these days. And as an example, cloud gaming has experienced a booming market these years. And more importantly, in our cloud gaming platform, which is called Start, mobile users are becoming the majority. And for network transport, these applications are brand new challenges. And compared to video conferencing, cloud gaming typically requires about 30 Mbps bandwidth and below 20 millisecond latency. And the upcoming XR applications have even more strict requirements. So it's challenging to achieve both high throughput and low latency at once, and especially for mobile networks. So how do these applications work? They can be depicted by this diagram. It's a closed-loop pipeline, consists of three parts: video frame generation and codecs. The encoding and decoding process is fast using some special hardware, and network transport, which is the most critical part because any delayed frame delivery, which is more common in wireless networks, can lead to a video stall. And video frames are generated in real time, depends on users' actions. So they are known in advance. We cannot store or pre-process them for any optimization. And last, the playback buffer at client side is relatively small. So we cannot depend on them to absorb any network fluctuations like we do in video-on-demand applications. So what's the problem now? As we can see that if you are using Wi-Fi networks to access our cloud gaming platform, the medium latency is pretty nice. It's below 30 milliseconds, but latency at the tail is horrible. It's beyond 200 milliseconds. And such long-tail latency could lead to frequent video stalls. And even a slight increase in video stall rate could lead to a sharp drop in our user playing time. So this long-tail latency must be addressed. So naturally, we want to ask what causes this long-tail latency, and do you have any more insights from your online data? And luckily, we do have three observations. And first, we want to talk about the bottlenecks lies in the wireless last hop. The link between your Wi-Fi AP and your device is vulnerable to wireless fluctuations, so the last hop RTT can sometimes be inflated. And in some dense Wi-Fi networks, this RTT can inflate to around 200 milliseconds, which is huge and disastrous. And traditional approaches to reduce latency in real-time streaming is to optimize congestion control, which is called CCA, or adaptive bitrate, ABRs. But they don't work in this scenario because, of course, you can reduce the sending rate timely at the server and get a pretty clear wide area network. But the last hop RTT still exists. And to demonstrate this, we force our online CCA to maintain some extremely low bitrate, I mean less than 1 Mbps. But long-tail latency still exists, and the distribution patterns are the same. So we can conclude that this phenomena is intrinsic to wireless path, and traditional ways can't just solve it. So our idea is simple: to bypass it and use multipath for real-time streaming. And what else have we found? We have some insights about the network characteristics during cloud gaming sessions. We use the word characteristics to describe video stall rate and its correlation to RTT inflation, which means P stall and P stall under the condition of some RTT value. And we find such characteristics vary greatly among different users. If you have a coordinate to record the relation between RTT and stall rate like this, and a user session maybe looks like this, and some other guy looks like this, and someone maybe like this. And if you plot all user sessions and overlay them as a heat map, you will get something like this. And this result indicates RTT inflation has different impact on different users, and we cannot just expect some general solutions suitable for all users. Well, that's a little disappointing, but we do have something promising. We find for individual user sessions, their characteristics remain relatively stable. We show the ks distances of such distributions between adjacent time windows and find the distances are very tiny. So in a simple word, the store rate and its correlation with RTT is stable for each user. So basically we have this diagram. We have inter-session variance and intra-session stability of network characteristics. So we can capture the unique characteristics of each user to use in our optimization. And last, we find users are very sensitive to cellular data usage. Our online survey reveals that users express strong will on the reduction of cellular cost. And traditional multipath transport schemes ignore this important factor and cause large cellular cost. So they are not practical. And on the contrary, we must consider cellular data minimization as a major concern in our design. So we can take a brief summary. We find last hop RTT inflation, so we want to bypass it using multipath transport. We find stable and unique network characteristics of individual user sessions, so we want to capture it. And we find cellular cost is of great importance, so we want to minimize it while using multipath. And here we have our three design goals, D1 to D3. However, there's a dilemma between D1 and D3, because more cellular data usage may bypass more RTT inflation of Wi-Fi and brings lower latency, but of course brings more cellular data cost, and vice versa. So what we want is a sweet area here to balance these two goals. How do we do that? Remember the unique network characteristics of a session. We capture it by deriving a state probability model and record the relation between frame delay and video stalls. And using this model, we can formulate when and how to use multiple paths as an integer linear programming problem. And we use the solution to the ILP to decide two multipath utilization schemes, frame level fast retransmission and primary path switch. I will talk about these two things later. And the ILP solutions brings all our goals together into this switch area, and that's our system, AUGUR. So what is our state probability model? And first, we divide the network statistics during the whole session into some states. And in AUGUR, we maintain two state spaces, the in-flight time of all frames and the in-flight time of the earliest active frame. We define state spaces in this way because we want to capture the frame latency distribution using the former one and the path latency distribution with the latter one. For example, in our edge server sending queue, we have 4 video frames sent out like this, waiting for X. And T1 to T4 is the time step when the frame is sent out. Now the earliest unactive frame is T1, so U2 only contains now minus T1, and U1 is empty because no frame is active yet. And maybe sometime later, T1 and T2 are act, so U1 now contains 2 in-flight frames, now minus T1 and now minus T2, and U2 is added a new value because T3 is becoming the earliest unactive frame, so U2 is added now minus T3. And now we already have some states. We want to define a probability model to correlate such state to video store events. We basically divide the overall video store probability into our states using some conditional probabilities, and therefore we can define our state probability model to be a set containing all these probabilities. I mean, the probability of video stores of each state and the conditional probability between them. Now we have a definition. How can we get and update such models at runtime? And in fact, the real distribution of these probabilities can be arbitrary and hard to describe at runtime. So we use our previous observation. The network characteristics of each individual user sessions remain stable for a period of time. So with this feature, we can approximate such distributions using frequencies of each state within a time window. And for each time window, we can update the estimation of our state probability model. That's simple. So with our model, we decide when and how to use multiple paths. So the basic idea is simple, as Wi-Fi fluctuations are minor cases, and we want to minimize cellular cost. So we use Wi-Fi as our primary path and cellular as a backup. And basically, we want a strategy to decide when to use the backup path. And in Augur, a strategy is a subset of the state spaces. We're asking at what states should we use our backup path? And what is this strategy? Remember, in our design, we have a dilemma. On the one hand, we try to use the backup path to bypass Wi-Fi RTT inflation, which means minimizing false negative rate, like I should have used the backup path, but I didn't. And on the other hand, we try not to use the backup path too much to reduce cellular cost, which means minimizing false positive rate, like I shouldn't have used another path, but I did. And combined with our state probability model and some mathematical derivations, please refer to our paper for details, we have something like this. And what is this? It's actually an integer linear programming problem, and by solving such problem, we can obtain a backup path utilization strategy and satisfying both D1 and D3. Now we're done. So we know when to use the backup path, but how do we do that? And in Augur, we have two state spaces, remember? U1 and U2. So we use the backup path in two ways, which means two sets of strategies. Because U1 contains frame latency distributions, and its corresponding state probability model describes the relation between frame latency and video store. So we have a strategy X1, which is a subset of U1, to determine which in-flight frames should be retransmitted. And unlike the traditional packet level or an RTL-based retransmission, we actively retransmit the whole video frame on the backup path, because at this time we conclude that this in-flight frame on the Wi-Fi path is never going to make it. It is going to cause video store, so we protectively retransmit it on the backup path. And U2 contains path latency distribution, so we have a strategy X2. It's a subset of U2 to determine when should we temporarily switch the primary path to cellular. And why do we do that? Because sometimes we can observe an abrupt capacity drop of Wi-Fi path, or even disconnections lasting for seconds. And in such cases, we can just rely on the backup path. So we put all things together. Our solution Augur looks like this. It runs purely on the server side and requires no modifications to the network or client. And first, we have a state monitor. It monitors and records the frequencies of four-mentioned states at runtime and approximates two state probability models in each time window into two state spaces. Then we have a multipath agent to decide when and how to use the backup path. It uses the state probability models as inputs and solves ILP problems continuously and obtains the two strategies. Strategy X1 decides frame retransmission, and strategy X2 decides primary path switch. So here we briefly present some emulation results of Augur. We use some traces collected from our user sessions and fit them into Mahi. We can see that when cooperating with Salsify, which is a real-time streaming CCA, Augur keeps pretty low tail latency, especially at 99.9 percentile, and as a result, it leads to a low store rate, less than 0.1%. But wait, what about this red and blue line? They don't look good, right? You know, when cooperating with GCC, Google Congestion Control, the performance of Augur is not promising. I admit that. This is because GCC is not suitable for real-time streaming, especially for cloud gaming, because a lot of works has approved that, and with the single pass, the 90 percentile latency is pretty high enough. And remember that Augur aims to bypass the last hop RTT inflation provided by a clear wide area network. So it should cooperate with a real-time streaming CCA like Salsify or SQP. And we do that, and cooperating with both CCAs against other multipath transport schemes, AUGUR keeps the lowest tail latency, and with a 99 percentile latency below 140 milliseconds. And as a result, it reduces the video store rate by nearly a magnitude compared to other multipath solutions. And more importantly, our multipath utilization strategy keeps the overall cellular data usage below 5%, much lower than other solutions. And finally, we have deployed AUGUR in Tencent cloud gaming server clusters for over a year. Our online CCA is Putica, which is a pretty good CCA tailored for real-time streaming, and was represented in session scheduling the network the day before yesterday. And we can see that AUGUR can effectively reduce long-tail latency and video store rate by nearly a magnitude with minimal cellular cost. And as a result, AUGUR brings nearly 20% improvement in user playing time, which means more money. And to summarize, we show that wireless fluctuations at Wi-Fi last hop leads to RTT inflation and long-tail latency in mobile real-time streaming. And we use multipath transport to bypass it. While users are eagerly to reduce cellular data cost, we encounter the problem of multipath utilization and cellular data minimization. We solve this problem by capturing sessions' unique network characteristics, deriving some stage probability models, and solving IRP problems. And AUGUR has been deployed in our cloud gaming platforms with promising results, and we believe it is an important step towards seamless mobile real-time streaming in the future. And thanks for all your listening, and I'm ready to take any questions.